Hey, okay, so the key to nailing this one down, um, we're interested in like say we have this tunnel and we drop something and it falls to the center of the earth and we know it's going to speed up, speed up, speed up, and then it's going to pass through the center of the earth and get to the other side and come back up. And we know that if we think about the motion of this thing back and forth, we suspect it's going to be something like a spring going back and forth. Okay, just like that. Now, the way we can find out if that's actually true is by realizing that for a simple harmonic oscillator, um, we have a linear restoring force. So F is minus kx. Okay, and then what we usually do is we say, well, that's MA, and so anyway, out of that we get omega is equal to the square root of k over m. Okay, so all that standard stuff right there. But the trick that we want to be able to do is to find out, okay, well, is there a linear restoring force actually? Okay, so we begin with Newton's universal law of gravity, and we sort of aim towards Hooke's law. All right, which sounds kind of weird, but watch what's going to happen here. So with Newton's universal law of gravity, the force is minus g m over r squared. Okay, now if we're in some tunnel, then that means the amount of earth below us is constantly changing. In other words, the mass below us is constantly changing. So we really need a way to talk about what's the mass under our feet, so to speak, if we're at different distances away from the center of the earth. And so we could say, well, our mass is really rho times the volume. Um, but that turns out to be rho times 4/3 pi r cubed. Okay. And then we can take that expression and dump it into here. And then what we're going to end up with is F is equal to minus G. And I'm just going to put little m over r squared, set all that stuff to the side. Plug in for BGAM. We got rho 4/3 pi r cubed. And here's what's really promising is that we lose all of those things. And so I have all these terms right here in front of a linear term, just like that. Okay, I'm running out of room on my screen, rats. Okay, so it's going to get a little tiny. I apologize. I didn't plan ahead very well. So let me write all that stuff out. So our expression for F becomes minus GM rho 4/3 pi r. And we want to massage that or force it to be some kind of K constant thing times a distance. And that's where we get our R from. Okay. And you can see it works out great. So all I really need to do is find out. So what do I have for K? Well, for K, I've got this stuff here. Okay, now in order to get omega out of it, we divide by m. All right, so this term right here is omega squared, just like that, which means that what we have for omega squared is g rho 4 pi over 3. Okay, so there's omega. And it's really interesting that ultimately it only comes down to the density of the planet. And of course, the universal gravitational constant. But anywho, there you go. Once you have omega, then you can get to the period T. Okay, because it's still omega is 2 pi times the frequency, so that's 2 pi over the period, et cetera, et cetera. So I'm sure you can chase it down from there. Okay?